Hi everyone, my name's Layla Mahmood and welcome to the first webinar of the series focusing on the fundamentals of rate transient analysis. In this webinar series, we will cover the fundamentals of RTA. We will go through concepts like the pseudo-steady-state inflow equation, type curves, multi-phase FMB, as well as some modelling. I'll include some software application to show how we put the theory we learn into practice. In today's webinar, though, we will cover traditional methods of analysis, an introduction to RTA, and some general concepts such as transient flow and boundary-dominated flow. We'll first start off with traditional methods of analysis to help give us a clear understanding of why we should be using rate transient analysis. One of the traditional methods of analysis is decline curve analysis. This was developed by ARPS in the 1940s. It doesn't use any flowing pressures, only uses production rates, and it assumes boundary-dominated flow. However, it's essential to have history or data in order to identify a trend and in order to predict the future. And what's the implicit assumption that we have there? It's that the well will continue to perform under constant operating conditions. We know that decline curve analyses are great for analysing production rates and forecasting future performance of wells to help determine EUR. We can base our curve fits on analogy, which would be other wells in the same field or pool. We can use the production trends of other wells to predict what will happen with the well that we are currently working on. There are some limitations of decline curve analysis though. We must assume constant operating conditions and boundary-dominated flow. The production rate is required to be declining. It's very difficult to conduct a decline curve analysis when the well is in plateau. And finally, there can be some uncertainty when you don't have enough historical data to work with, so it's important to have enough data to identify a trend. So the behaviour of the production data can be characterised based on the way in which the nominal decline rate varies with rate, based on the value of the decline exponent constant b. With exponential decline, this will result in a straight line on a plot of flow rate versus Q production, and b value is equal to 0. With hyperbolic decline, neither a plot of flow rate versus time or flow rate versus Q production will result in a linear relation. The b value is in between 0 and 1. And with harmonic decline, on a plot of flow rate versus time, there's no linear relation. On a plot of flow rate versus Q production, with the rate set to logarithmic axis, it will result in a straight line. The b value for harmonic decline is equal to 1. So what's the meaning of these different stems? The exponent b is related to the drive mechanism. The b values here are approximate and are subject to change. So with single-phase liquid production with oil above the bubble point, this will occur when b is equal to 0 and will give us an exponential decline. With solution gas drive, the reservoir pressure is lower and the decline rate is lower, so the b value is approximately 0.3. With reservoirs of different energy systems, the b value is likely to differ. For example, you have an approximate b value of 0.5 for water-drive reservoirs and between 0.4 and 0.5 for gas wells. So the higher the energy systems, the higher the value of b. So this illustration here nicely shows us the implications of lack of historical data. We can see the curves can all fit the data nicely, but can be extrapolated at different EUR values. So which decline curve analysis or EUR value would you say is correct for this data? Well, actually, there's no correct answer. So there's always a degree of uncertainty with forecast, and in order to make a reliable judgment, enough historical data is needed. So let's jump into the software for our first example. It's an example where we'll be using decline curve analysis to show us where we have over-predicted reserves and under-predicted reserves. So I've jumped into the software for our first example. In this example, we'll take a look at us over-predicting reserves using decline curve analysis. So I'll start off by creating a decline curve. It's a gas well, so I'll do a simple gas rate versus cum gas decline. Now here we can see my gas rates on this plot. I can lock in my b value to 0 to ensure an exponential decline. And I can lock that in place. So what's this plot showing us? This is showing us that by looking at our gas rates here, we can get an EUR of around 9.5 BCF. So let's then take a look at the flowing material balance plot and see what that gives us. So the flowing material balance will take into account both rates and pressures. So this is the FMB, or flowing material balance, a plot of normalized rate versus normalized cumulative production. The FMB is one of the most common analysis methods used in RTA. We'll examine the theory of how FMB works later on in the series, but for now, let's take a look at the results it's giving us. From our flowing material balance plot, we can see that we have an original gas in place of around 6 BCF and an EUR of 5 BCF based off of an 80% recovery factor. So that's quite a big difference. The flowing material balance is giving us an EUR of 5 BCF, whereas the gas cumes, by just looking at the rates, is giving us an EUR of 9.5 BCF. So there's a difference of around 4.5 BCF. So in the decline analysis, we're assuming that the bottom hole flowing pressures will remain constant throughout the life of the well, unlike in the FMB, where it takes flowing pressures into account and how they vary through time. We can also apply our flowing pressures on the gas cume plot when we have an abandonment pressure of 225 psi. So here we can see that I have extrapolated my flowing pressures up to the abandonment pressure of 225 psi. At this abandonment pressure, we get an EUR of around 4.7 BCF. So from this plot, we can see that the EUR from our rates cannot exceed the abandonment conditions, and therefore cannot exceed the EUR from our abandonment conditions of 4.7 BCF. So the flowing pressures do help give us a context for what the rates are telling us.
So let's next take a look at an example where we are under-predicting reserves using decline curve analysis. So like I did with my previous example, I'm going to start off by creating a gas rate versus cume gas plot and create my decline on this plot. So what can we see from this decline here? We can see that we have an EUR of around 3 BCF. Now this would be a reasonable interpretation, and it looks like an exponential decline on this rate versus cume plot. Let's now take a look at the flowing material balance. Now from the flowing material balance, we can see that it gives us an original gas in place of 24 BCF and an EUR of around 20 BCF based off of an 80% recovery factor. So this time we can see that we have an EUR of 20 BCF compared to an EUR of 3 BCF from the gas cume plot, which is a massive difference. So you do need both the rates and the flowing pressures for the full analysis. We can see that the decline is just telling us that we will only recover 3 BCF, whereas the FMB is telling us we can recover a lot more. So let's apply our flowing pressures on our gas cume plots and see what we can identify. So you will notice something happening here with the pressure trend in blue. We can see that the flowing pressures are increasing, caused by an increasing back pressure impacted by other wells coming on stream in the gathering system. This rate versus cume is not necessarily incorrect, but it doesn't show the full potential of the well.
So to see what upside potential there could be from this well, we have done some modelling and history matched the production, as you can see here on our analytical model. Now that it's history matched, we can try some what-if scenarios with the forecast to see if we can improve production. One scenario would be if we can lower the back pressure of the well, say by wellhead compression, and see what the resulting forecast would look like. So in this example, we've lowered the sand face pressure and removed the back pressure, and as you can see, the production has greatly increased. So we can see the analytical model is giving us an EUR of 13 BCF, and that's telling us we can recover an extra 10 BCF of production. So RTA in this case was helping to uncover a large amount of potential from the well.
Now, empirical decline analysis does make some major assumptions. The factors causing the decline remain unchanged during the forecast period. Factors that affect the decline rate are reservoir conditions such as reservoir pressures, production from neighbouring wells, relative permeability, as well as operating conditions such as wells with enhanced oil recovery techniques or stimulation, tubing sizes, etc. To understand this a little bit better, let's take a look at the plot at the bottom here. So we can see that the first section of the data has not been affected by any reservoir or operating conditions, as the data does not show many large fluctuations. Whereas in the second part, there is a big difference, and this is due to a change in reservoir conditions. In this case, we can identify water injection. So let's look at another traditional method of analysis, and this is volumetrics. So volumetrics are a useful method for evaluating fluids in place when performance data is not known or not available. This method does have its limitations though. Volumetrics is limited because it relies on inputs that are not usually well known. One input that has a very large impact is the areal extent of the reservoir, and as this is not normally well known with a high degree of confidence, it can have a big impact on the oil or gas in place. If these models are then relied upon without incorporating performance data, then how do you know that your model is actually representative of the fluids in place? The final traditional method of analysis we'll look at is static material balance. Now, material balance has been around for many years and is a traditional method for evaluating fluids in place. It's based on an analytical model and it's independent of operating conditions. It's complementary to the other traditional methods such as decline curve analysis. The material balance calculation will also generate original hydrocarbons in place. Conceptually, for this type of analysis, the type of data required would be obtained by shutting in the well and measuring the average reservoir pressure at different points in time during the life of the well. If we can get enough measurements through time, then we can use them to extrapolate to the original gas or oil in place. The static material balance does, however, require the well to be shut in. The easiest way to illustrate the concept of material balance is to look at the very well-known procedure, and that is the gas material balance. This is one of the simplest forms of the equation and is something taught routinely at university, and as a procedure, this is something petroleum engineers should be very familiar with. The gas material balance is a P over Z versus Q production plot. So what we do is we measure the average reservoir pressure at different points in time through the life of the well and plot the P over Z versus Q production. If the pressures are truly representative of the stabilized reservoir condition, then the extrapolation of the line of best fit through the data gives the original gas in place. There are some important limitations to the material balance formulation as I have presented it. The most obvious one is that the well needs to be shut in, which means lost production, and most operators don't want to shut in the well if they can help it. In lower permeability systems, the time required to shut in the well and get a representative reservoir pressure may take too much time and therefore too much lost production. Regardless of the permeability of the reservoir, if the well, and this happens a lot, is not shut in for long enough, then the average reservoir pressure determined from the build-up analysis may not be representative of the actual average reservoir pressure because the reservoir is not fully stabilized. If this is the case, then there can be errors in extrapolation. In addition to the limitations already outlined, when doing the material balance, we are often dealing with sparse data, and so it can be difficult to recognize a trend in the data, and this can lead to uncertainty of the original fluids in place. Build-ups may be performed as little as once every 5 years, and so it's difficult sometimes to have decent data sets to work with. Let's move into the software and take a look at an example of an oil volumetrics case and a gas static material balance.
So I've jumped back into the software for my volumetrics example on an oil well. We can see that I've already conducted my oil rate versus cum oil production decline curve analysis, and that's given me an EUR of around 1.2 million stock tank barrel. So the next step then would be to do a volumetrics analysis. Now, volumetrics will give your original hydrocarbons in place, and the information required for volumetrics is rock properties as well as fluid saturations and properties. And we can see all of that information displayed here. It's also worth mentioning that in the Editors tab, this is where all of your data resides, so all of your reservoir properties and data will be entered in here, And once it's entered in once, all of the analyses on this well will pull off of this data, so you don't have to keep entering your data. So back to my oil volumetrics example, we can see that the only piece of information that's missing from this example is the drainage area. And this is a parameter that's usually given to us by a geologist. I know for this well that the drainage area is 500 acres, so I can enter that in. And we can see on the left-hand side here, this will generate out my original oil in place of around 10.6 million stock tank barrel and my cumulative oil production of around 1.1 million stock tank barrel. Now, what we can do is we can combine our results from my volumetrics analysis to the decline analysis in order to generate out a recovery factor. So by combining the two analyses, we can see that it's generated out a recovery factor of 11.4% based off of the 500 acres of drainage area. So we can see that by doing our volumetrics, it's given me my original hydrocarbons in place as well as my recovery factor. So we can now move on and do the example for static material balance. So now looking at an example of static material balance on a gas well, you can see that I've already created my gas rate versus cum gas production decline on this well to give me an EUR of around 20 BCF. So let's then go ahead and do a static material balance. Now we can see the pressure points already, and we can see that reservoir pressure is decreasing as gas is being removed. Now this works in a similar way to decline as it creates a best fit through the points. So it generates out the volumes in place, and we can see that the volumes in place, or the original gas in place that's been generated, is 24 BCF and a normalized gas production of around 18 BCF. Now, similar to my volumetrics example, I can link this to my previous decline curve analysis in order to generate out my recovery factor. So I can simply drag and drop into my decline to generate a recovery factor of 80.9%. Now I'm also going to do a volumetrics analysis for this well. So I can simply do a gas volumetrics. Again, I can see all of my information already entered. All I need to do is enter in my drainage area. I know for this well it's 550 acres, so I can enter that in. And it will generate my original gas in place. Now, similar to before, I'm going to link this to my gas cum analysis where I've already got my material balance. And it's important to note the area here and how it will get back calculated. So we can see here that my drainage area has been back calculated. So the software will always honour the material balance calculation, and it will back calculate the area based on the volumes in place from the material balance. Now the software also has a pressure versus time material balance sheet. Now this is very useful when grouping wells to see if they're in the same reservoir. As wells that are producing in the same reservoir will have the same average reservoir pressure over time.
Now moving on to an introduction to rate transient analysis. So what is rate transient analysis? So rate transient analysis uses both the rates and flowing pressures and is based on physics. It's not an empirical methodology. In fact, it's based on physics, and we are trying to understand the fluid flow in the reservoir. This is something that pressure transient analysis has been doing for many years. RTA is based on the same theory as PTA, just we're using it in a slightly different way. Production analysis is really reservoir signal extraction and characterization, and involves taking a large amount of data and then analyzing it to see if there's a reservoir signal that we can extract. We can get the same deliverables such as production forecasts and EURs, but now we also get original gas or original oil in place, which is derived from performance data. So we can then get a performance-based recovery factor, which will allow us to easily do screening to see which wells may have a low recovery factor, and hence see which wells may need more attention or potentially production optimization. Drainage areas can also be determined, and as such, if you know the spacing the well was drilled on, you might want to carry out infill drilling and drill some more wells. In addition, this production analysis will also give you parameters such as permeability and skin. So why should we use rate transient analysis? One of the main reasons for using modern production analysis, or RTA, is to evaluate reserves with greater reliability, and sometimes there is an upside that you didn't see with traditional methods. It can also actually avoid you overbooking or underbooking reserves through decline analysis, and so it can uncover some errors. Production engineers may use RTA to monitor production performance, and once they have got a good model match and understand the reservoir, they can update this model going forward and see if the actual performance matches the performance of the model. RTA can be used as an alternative to full pressure transient analysis to characterize the reservoir, and can be much more economic as the well does not need to be shut in. This is actually very important in low permeability reservoirs, as it can take a lot longer for the pressure to build up in these reservoirs. RTA also allows you to see much further into the reservoir than PTA may normally allow. Another reason to use RTA is the minimal cost that we have associated. The data should be being collected as part of good production practice, and then these techniques can easily be implemented into an engineer's workflow with minimal cost. With the data in Harmony Enterprise, it may only take an engineer to get a type curve and model match in, say, 10 to 20 minutes, and then they have an answer and can make a decision. So here there is a very low cost of effort to get results, especially when you compare the time it would take to do a full numerical simulation. That's not saying that you shouldn't do a numerical simulation, but RTA acts as a very good precursor to it and also provides quick checks to the continual health of the well. You'll hear us talking about reservoir signal, and by this I mean the expected change in rate if the wellbore pressure is held constant for a time, or the change in flowing pressure if production rate is held constant for a time.
Now, well performance analysis is any kind of production, pressures or rates that come out of the wellhead and that we can analyse on a time basis. The data on the right represents the raw data that we import into Harmony Enterprise. Using RTA tools, we want to conduct an interpretation of our data. We characterise the reservoir signal with various parameters, such as permeability, fracture half-length, volumes in place, etc. Once we've interpreted our data, then we can recreate the more complex waveform from the simple reservoir signal using the parameters we have extracted. Our goal is to verify our interpretation by being able to recreate the historical data through modelling. So our recommended approach is to use all the traditional methods as well as rate transient analysis. It's much more complete and useful to analyse both the rates and the flowing pressures together. And why is that? Firstly, no single method always works. It's always a good idea to use multiple methods to verify and be confident with your results. Also, production data is varied in frequency, quality and duration, and time constraints and well counts also need to be taken into account. Now, in the past, there was on one side the well testing methodology, and on the other side, decline curve analysis. Now, though, modern production analysis, or RTA, is the integration of knowledge that allows you to get some of the well test side and some of the empirical side, as well as producing its own deliverables like performance-based recovery factors, flow regime characterization over the life of the well, as well as being able to analyze transient data from lower permeability reservoirs.
So moving on to look at some general concepts, starting off with transient and boundary-dominated flow. So we'll explain this using a simple example. If you imagine throwing a stone into a pond, this will create ripples in the water, and the ripples would eventually reach the boundary of the pond at different pulses, and they will start off small and get larger and larger until they reach that boundary. Similarly, in a reservoir, you have the boundaries of the reservoir. And the red circles here represent the pressure transient pulses moving out into the reservoir, with the green circles representing the pulses reaching the boundaries of the reservoir, and therefore boundary-dominated flow. So transient flow. This has been the domain of pressure transient analysis. Transient itself means there's not enough time to reach the boundaries of the reservoir. It's an early time or low permeability flow. Transient flow occurs in low permeability reservoirs that may be producing for a very long time, and the pressure pulse won't move far out into the reservoir. It's a flow that occurs while a pressure response or pressure pulse is moving out into an infinite or semi-infinite acting reservoir, and it has not hit all the boundaries of the reservoir. Just like a fingerprint is a unique thing for everyone, transient flow is like the fingerprint of the reservoir. I might have two wells drilled side by side in the same reservoir, and their transient responses might still be different. It's a unique combination of well and reservoir together. Examples of transient flow would be radial, linear, and bilinear flow.
One of the most common transient flow regimes experienced in conventional reservoirs is radial transient flow, displayed here in normalized rate form for your reference. It's an early time equation for infinite acting radial flow, which is applied at the very beginning of production and may stretch out longer depending on how low the permeability is. Permeability and skin are solutions of this equation.
Let's take a look at the radius of investigation. The radius of investigation will tell us how far we've seen into the reservoir. We know in transient production, there's a finite distance that we've observed into the reservoir and we haven't seen beyond it. And we may want to capture how far that is, perhaps to predict how big the drainage area will be or how long it will take to reach that drainage area. The radius of investigation equation allows you to determine how far the pressure transient will move out at a given time for a particular set of reservoir properties. So these two wells are the same size and in reservoirs with the same net pay and reservoir properties, but they have different flow rates. At a given point in time, which well will have a greater radius of investigation? The answer is the same. They'll both have the same radius of investigation. The hydraulic diffusivity, in fact, will control the radius of investigation. The hydraulic diffusivity is, in fact, independent of rate. When you produce from a reservoir, a pressure pulse moves out through the reservoir. The speed at which the pressure pulse moves out has nothing to do with rate, but depends on the reservoir properties, such as permeability, porosity, viscosity, and compressibility. For example, the lower the permeability, the slower the pressure pulse moves out, and the smaller the radius of investigation for a given amount of time. Now let's look at boundary-dominated flow. Boundary-dominated flow is a late-time flow behavior when the pressure pulse has reached all the boundaries of the reservoir, and this typically dominates long-term production data. Here the reservoir is in a state of pseudo-equilibrium and physics reduces to a mass balance. It gives us information about reservoir pore volume. Specifically, let's look at a case where we flow a well at constant rate. Then the pressure profile in the well would look something like this. When a well is flowing, we have a drawdown pressure PWF and a reservoir pressure P bar. The reservoir pressure is greater than the drawdown pressure.
In boundary-dominated flow at constant rate,
as we go through the successive time steps, the pressure profile in the reservoir has exactly the same profile as the previous step. This behavior is what is fundamental to the concept of boundary-dominated flow, and this is what makes rate transient analysis work. When you're in boundary-dominated flow, pressures drop in the reservoir by the same amount anywhere in the reservoir. The pressures at the boundary will be dropping by the same amount as near the wellbore.
So here is the equation that represents boundary-dominated flow and is also known as a pseudo-steady-state equation. It consists of two parts, the pressure drop due to depletion and pressure drop due to reservoir flow. We'll revisit this equation and the transient ones a little later in the series.
So that brings us to the end of today's webinar. Thank you for tuning in to the first webinar of the series. In the next webinar, we will cover the pseudo-steady-state inflow equation and we'll go into the theory of type curves.